How do you know a structure is determinate or indeterminate? The key here is in equilibrium. If you can use the equilibrium conditions to analyze the structure, then it's called determinate. If you cannot, then it's called indeterminate. To further describe the indeterminate structure, we use degree of indeterminacy, which is defined as the difference between number of unknown reactions and the number of equilibrium conditions that you can establish. To analyze indeterminate structure, we need to set up additional equations. I'm going to introduce a force method. The force method uses forces as unknown, or called redundant forces. And the number of redundant forces should be equal to degrees of indeterminacy of your structure. And we can establish additional equations through compatibility or least work principles. So the force method is also known as the compatibility methods or the flexibility methods or the methods of consistent deformation. Let me use this beam as an example. This beam is clamped on the left and roller support on the right. So it has 4 reaction forces, 3 on the left and 1 on the right. And this is a 2-dimensional structure, so we can only establish 3 equilibrium conditions. So as a result, this is a 1 degree of indeterminacy structure. So we need to choose 1 redundant force. So let me choose the reaction force at B, vertical, as a redundant force. So you can consider that this structure is acted by the point force of P at the midspan, as well as the support reactions at B, By. Using superpositions, you can analyze this structure separately. First, under the reactions of P, and then second, under the actions of reaction force By. You can calculate the displacements at B due to P, as well as formulating displacements due to By. And if you realize that this is a roller support which is refrained from vertical displacements, so delta B should be equal to 0. So according to superpositions, the displacement at B due to P and displacement at B due to By superimposed should be equal to 0. So here, this is the compatibility equations that we can establish. This equation contains an unknown redundant force, By. So we can use these equations to solve for By. Now in practice, as it's a little bit difficult to find displacement due to By, as By is an unknown. So we usually assume that I apply a unit force at B, calculate the displacement due to this unit force, and then take that multiply by the unknown redundant force, By. So the compatibility equations then leads to this expression. So through these equations, then we can find By. Here's another example. So this is a continuous beam sitting on a hinge on the left. Middle point is roller support, and the right is another roller support. So very obviously, this is 1 degree indeterminate structure. So you can choose either the reaction force at D or reaction force at B as the redundant force. You only need to choose 1 redundant force because this is 1 degree indeterminate structure. So let me choose By as a redundant force. And then again, using superpositions concept. First, apply the external force without By. Calculate displacement at B, and then apply a unit force at locations of B. Calculate the corresponding displacement. And displacement superpositions should be equal to the displacement at B, which is equal to 0. So that leads to this compatibility equations. So again, the only unknown in these equations is the redundant force, By. So you can find By from that equation. So let me show you how you can use the same concept to analyze a higher degrees of indeterminacy. In this case, this is 2 degrees of indeterminacy. I have a beam clamp at the left. Middle, I have a roller support, and on the right, I have another roller support. This is a 2-degree indeterminate structure. So I can choose the redundant force Cy and Ey. So first, I remove the 2 redundant forces and apply only the external force, calculating displacement at C and displacement at E. Then I apply the redundant force one by one. First, I apply a redundant force at C, vertical upward, with 1 kilonewton. Calculate the corresponding displacement at C and displacement at E. Then I apply another redundant force, Ey, with dimensions of 1 kilonewton. Calculate the corresponding displacement at C and displacement at E. Take the last 2 results multiplied by the redundant forces, Cy and Ey respectively, and then superimpose all 3 results at 2 locations, location C and location E. Because these 2 locations, they are sitting on support, so they cannot have displacements. So you have to force the displacement, superimpose, and then go back to 0. So here are the compatibility equations that you can establish. So from these 2 compatibility equations, you see that there are 2 unknowns, Cy and Ey. They are the redundant forces that you chose. So you can use the 2 simultaneous equations to solve for these 2 redundant forces. You can also establish additional equations through least work principle. So let me introduce this least work principle from Castigliano principle. Assuming that I have a cantilever beam under 2 forces, P and F. So according to Castigliano theory, I can calculate displacement corresponding to the directions of F. How can I do that? I just follow these equations. I first calculate strain energy, U, equal to integrations of m squared over 2ei dx, where m is the internal bending moment, which is a function of P and F. So you find internal bending moment substituting to get the expressions for strain energy, and Castigliano theory tells you that if you take strain energy partial differentiate with respect to F, and then substitute the magnitude of P and F, then you get displacements along the directions of F. So that is Castigliano theories. So this theory can tell you the displacement if P and F are given. Reversely, if displacement is given, can we use the same equations to calculate, for instance, if F is unknown? The answer is yes. All you need to do is, instead of directly calculating from left to right, you can just substitute displacement equal to 0, and then assuming that F is an unknown, so you can find the unknown F from this single equation. So this is the so-called least work principle. Now, why is it called least work principle? Because mathematically, rung U, rung F equal to 0 is a tangential line along the curve of strain energies. When that is equal to 0, which indicating that the strain energy is a minimum. So the least work principle says that the magnitude of redundant force must be such that the strain energy stored in the structure is a minimum. That's why we call this least work principle. As the least work principle and Castigliano principle has a very similar formula, so you might wonder what is the relationship between the 2. So let me use the virtual work principles to explain the relationship between the two principles. So take this beam structure as an example. This is a cantilever beam under two forces, forces P and forces F. The displacement along the P direction is delta P, and displacement along the F directions is delta F. So I can express the internal bending moment, which is a function of P and F, and then obtain the strain energy expressions, which is, again, a function of P and F. As these two forces are external forces, they will do work. So the work will be a function of P and F. Next, if I introduce a support at F, constrain that point from moving vertically, then the displacements along the F directions will be equal to 0. So as a result, F cannot do any work into the structure. So the work expressions will be purely functions of P. So I can relate P to U through work and energy principles. So this described the structure under equilibrium. Then I can introduce perturbations into this equilibrium structure by introducing delta F and delta B correspondingly at F and P location. So substitute this perturbation force into work and energy principles. Then this is the equation. I can do Taylor series expansions and retain up to the first order. So here. So on the left is the work expression. On the right is the strain energy expressions under perturbations. And according to work and energy equations, so the first term on the left and the first term on the right, they will be canceled. So this is perturbation work, and this is perturbation strain energy. So assuming that the structure is linear elastic, which means that P and displacement follow a linear relationship, then work is equal to P squared over 2K, K being the slope of the P delta relationship. Then run W run P is equal to P over K and is equal to delta P. So substitute this relationship to the left-hand side of the equations. Rearranging the equations, then you will get this equation. As perturbation delta P and perturbation delta F, they are independent. So the bracket here has to be equal to 0, and so is the coefficients in front of delta F should be equal to 0. So here we have two equations simultaneously established. From the bracket is run U run P equal to delta P, and from the coefficients of delta F is run U run F equal to 0. So here we have Castigliano principle for the first equations, and then we have the least work principle for the second equation. So from this virtual work principle derivations, we can establish both Castigliano principle and least work principle together. So the key here is F is a force that does not do any work into your structure. So if you have a force that cannot do any work into your structure, then it should follow the least work principle. That is, run U run force equal to 0. If, on the other hand, the force will do work into the structure, so when you do run U run force, it should be equal to displacement, corresponding displacement to that force. So that is Castigliano principle. So to summarize, I can establish Castigliano principles and least work principle simultaneously in one structure. Use this structure as an example. This is a cantilever beam on the left, but in the inside the span there are a few roller supports. So the reaction from the roller support are labeled as F1, F2, etc. External force P1, P2, etc. So you can establish the strain energy expressions, which will be a functions of external force P as well as reaction force F. So it depends on whether that particular force will do work into your structure. If yes, then when you do wrong U, wrong force, it should be equal to corresponding displacement, which is Castigliano principle. If that force cannot do any work into your structure, when you do wrong U, wrong force, it should go to 0, which is the least work principle. Before I end this part, I want to leave you with some questions. So assuming that I give you a cantilever beam, but on the right-hand side, I connect it to a spring. So I apply a concentrate force, P, and there is a reaction force coming from the spring, I call F. So I want you to think about the following questions. First, if I take wrong U, wrong P, is that equal to displacement at P? Second question, if I take wrong U, wrong F, is that equal to 0? Third question, I know that at this end, the right-hand side, I'm going to see vertical displacement. How can I obtain this vertical displacement?